Okay, so we're going to talk about thermodynamics, and today, probably today and tomorrow, what I'm primarily going to be doing is talking about system definitions. These are the things that allow us to address problems in a thoughtful and mathematical fashion, and we're also going to go through some basic mathematics. A lot of people think thermodynamics is terrible math, and it's really not. It's just that between the time when you took your multivariable calculus class and when you took your thermal class, there was some loss. And we'll go through all the math you need for thermal. It's just really not that bad. So, beginning system. The system is the region of space within the universe that we're interested in. Region of interest. And this system, it lives inside the universe. The universe is all known matter, energy, and space. So basically, anything you point to is inside the universe, and our system resides inside the universe. Now, the thing that allows us to talk about thermodynamics in an effective manner is that the system will interact with the universe. So the picture that you can draw, or the picture that I draw, is this. And then I draw system, and then we have this. Is in contact with the universe through some type of wall. And this wall controls how the system interacts with the universe. So, for example, we can have a wall that is impermeable rigid and insulated and in that case matter, work, and heat do not pass through. Now, if we change this wall and we say that our wall now is impermeable, insulated, and flexible, well, now it's impermeable, so matter can't pass through. It's insulated, so heat can't pass through, but it's flexible. So in principle, it can bulge into and out of the universe, meaning that work can be done to the system or by the system. If we have a wall that is rigid, conductive, and impermeable, then we can have something where heat passes, work does not, matter does not. Conductive, flexible, impermeable, matter cannot pass, work and heat can, and lastly, you have an impermeable wall, then matter can pass in and out, and so can work and heat. The think about having little holes in here, if molecules pass back and forth, those molecules can do work, and they're also going to be carrying energy back and forth. So anytime you have a permeable membrane, then it becomes an open system. So anything you have, you've got a bottle of soda. The bottle of soda can be thought of as a system. The bottle of soda is closed. I can squish it so I can do work, and this is not very well insulated, so heat goes in and out. A cup of coffee, you got an open lid, a closed lid, open lid, then gas can escape. But we're basically playing a game in which we look at something and then we draw walls around that and we define how that system will interact with the world around it. This is all okay? So when we're looking at our system, we look at it and we say, what are its properties? And we list a set of relevant properties. Relevant macroscopic properties. These are our state variables. Let's see. That. Those are state variables. The state variables define the state system. And I say relevant, you talk about annealing a metal, you say, well, where was the moon? The moon was over here. Did it impact the solidification of the metal? Yes, it did, but not enough for us to care about. So the position of the moon is not typically accounted for, even though it does exist in the universe. In our definition of the system, we're not paying attention to that. Now, talking about this state of the system, as I just defined it, this is called a macro state. And when in thermodynamics we use the word state, typically that's code for a macro state. There is also a microstate. Now, the microstate's important, and we're going to talk about that later in this class. The microstate, this is the atomic that make up macro state. Is basically how the atoms arrange themselves to give us a certain macrostate. Now, in the room right now, we might say the air in the room has the state variables, the temperature and the pressure, and the volume. And if we take a snapshot, we know where all the molecules are. But we wait a second, take another snapshot, they're in a different position. The microstate has changed, but the macrostate has not. And in fact, there are many microstates that lead to the same macrostate. Right? There's actually almost an astronomically large number of ways the molecules can arrange themselves in this room and give us the same temperature and pressure. So, kind of give you a hint about what's coming. When we talk about entropy, one way to think about entropy is the number of microstates that lead to a certain macrostate. Right? If you want to think about it as flipping coins, if the macrostate is the number of heads in the box of coins, and the microstate is the number of ways you can arrange those coins, there are many, many more ways to get a 50-50 combination of heads and tails than there is to only get all heads up. So the entropy is the number of arrangements that will give you, at least from a statistical perspective, the number of ways that you can arrange microstates to achieve macrostates. So when we talk about our macroscopic properties, typically there are a fairly small number that are actually relevant. And many of these variables are dependent on each other. So within these, I should say, only the independent variables are important. So let's talk about an example. Let's think about a closed, isolated box that contains a single component ideal gas. I've got some box that's closed and isolated so it doesn't interact with the outside world. It's got some ideal gas inside that. If you want to think of ideal gas, you can think of, say, helium gas, right? By ideal, I say no He2. There's no chemical reactions that are occurring within our gas, right? So basically, you want to think of these as a bunch of billiard balls that are bouncing around and banging against each other. That is our gas. Now, the state variables that are important. Actually, this is not very good pens. Change colors. Try red. There. The volume. We've got the pressure, and we've got the temperature. Variables B, P, T. But they're not independent, right? Only two are independent. So for our example, we're going to pick T and P as our independent variables, which means that volume can be written as a function of temperature and pressure. Okay, so we've got this example. Let's talk a little bit about this interrelationship between the state variables. We have a set of special equations that are called equations of state. And an equation of state is an equation in terms of the state variables that equals 0. So it's some function, in this example, of pressure, volume, temperature, and it's equal to 0. That is an equation of state. Now, your textbook tells us that we can write volume as a function of pressure and temperature. And this is, and let's call this EOS. This is an equation of state. But something that I think a problem with the way that we teach people about thermodynamics is we say volume is an equation of state. And it is. But the reason it's an equation of state is because we have a function of pressure, volume, and temperature is equal to 0. And we can take and arrange this so we get volume on one side, temperature and pressure on the other, which gives us volume as a function of temperature and pressure. So don't think there's something special about volume that makes it an equation of state. We could just as well written temperature as a function of volume and pressure, or pressure as a function of volume and temperature. This is what makes it an equation of state, the fact that we can put them all together on one side and have a 0 on the other side. So here though, we've decided we're going to pick pressure and temperature. And if we pick pressure and temperature, what that means is that we have some surface here, which is our volume as a function of pressure and temperature. And at some given pressure and some given temperature, we have some volume at pressure 1, temperature. Pressure 1, temperature 1. Now, notice the way I drew this, and as a consequence of this as well, it's single valued, right? This is a single function defined in pressure temperature space. It doesn't fold back on top of itself. You don't have more than one choice. So these guys are essentially single valued. And then that's something which is handy. What's also nice about this is the state. So this picture, so there's our phase space. Within our phase space, D1, the 1 here too, these are 1, depends only on T1 and P1. So it doesn't depend on how you got there or anything that happened before, right? It's like you walk into a room, you take a picture of the box, you know what the volume, pressure, and temperature is, and that's all you know. You don't need to know the history. You don't need to know or even where it's going after this. So that means that if we have at some point, and we change the pressure, the temperature, to some other point, that works. Or we could have gone a different path. Doesn't matter. Moving from state 1 to state 2 is going to be path independent. It only depends on where you wind up. Is this all okay so far? Okay. So now we're going to take a little bit of a mathematical divergence to give you some of the math review from your undergrad multivariable calc class, and then we'll take the next step talking about our phase space. So, mathematical review. So consider three variables. I'll call these x, y, and z. And let's say those three variables can be expressed in a function f of x, y, and z is equal to a constant. 0 is a constant, which, by the way, makes this really handy for us. But mathematically, it just has to be a constant. Well, if we have this, then we can write this infinitesimal change in x is equal to the partial derivative of fx with respect to y, holding z constant, times the infinitesimal change in y, plus partial of x with respect to z, holding y constant, times the infinitesimal change in z. So this means hold z constant. And again, to remind you, back when you're taking multivariable calculus class, that if you had a partial d by dy of y squared plus yz plus d squared, that was equal to 2y plus z. So this is our x. So you're taking the derivative of the y terms, and what z was, you're treating that just as a constant. So that is basically a reminder for you. In this class, oftentimes I find myself writing and I leave these out accidentally because we're only dealing with three variables, so clearly z is being held constant. But you can look at if it happens or fill it in your notes. But nonetheless, that's what that means. And this is how we write out this differential. And then we can similarly write the differentials. I'm gonna erase this. Similarly, write the differentials. dy is equal to dy dx d dx plus dy dz x dz, and dz equals dot 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 dot. You can fill in the blanks there, right? These three, sorry, total infinitesimals. Yeah. So this lets us write out those. Now, we also have these rules that let us mix and match these partial differentials. So for example, we have dz dx, a constant y, multiplied by partial of x with respect to z, constant y, and those, in terms of bad physics math, cancel each other out. Bad physics math actually gets a lot done. Mathematicians hate it, but this is true. It's also true that we can now write, it also gives us that dz dx y is equal to 1 over dx dz y. And another useful tool is this so-called triple product rule. That tells us that dx dy function of z times dy dz as a function of x times z dx as a function of y is equal to -1. And we can use this to give us, this will give us things such as dy dx as a function of z is equal to negative dy. I'll move this up here. We're almost out of time, so I'm going to finish up the mathematical review, and then we'll come back to the science in a second. So this will give us, as saying, dx dy as a function of z dx. dz dx is a function of y is equal to negative dz dy function of x, and dy dx of z to negative dy dx to z is a function of x over dx dz as a function of y dx y z dy, etc. So in your textbook, chapter 4, they go through a bunch of these relations. The important thing is they only come from like 2 places, right? We have the total differentials, which we wrote out, and that has to do with the fact that we have a function of our variables, those 3 variables, which turned out to be our state variables, that are equal to a constant. We have this relationship, and we have this relationship. And from all of those, you get all of these kind of screwy partial differential relationships that you can use to transform between partial derivatives. And what you'll learn in the next lecture is that what makes that useful is that each of these partial derivatives are actually measurable quantities. The partial derivative of free energies with respect to state variables are things such as heat capacities. And this will let you transform between those. If you look at your textbook, I think it's chapter 4, maybe it's chapter 3. They go through a whole chapter on this, and they make it seem a little more complex than it really is. It's really not that complex. There's 3 relationships, and then you just sit down with a pencil and paper, and you move through these until you get what you want. So we'll talk about that in the next lecture. Let me double check here. So we'll pick up in the next lecture, and we'll move from the little bit of math we did here, the math review, back to talking about state variables. Any questions about what we've done or what we're going to do? Supposed to wait 10 seconds when I ask these questions. I've been told, yeah.
I came late, I'm sorry, but I have a question regarding the course, the content of the course. Is it going to cover the thermodynamics of molecular systems?
Not explicitly. So what I'm going to be teaching is, I would say that kind of the peak here is understanding phase diagrams. Understanding phase diagrams means understanding the thermodynamics of mixing. And the thermodynamics of mixing comes from all of this. Now, it can be applied to molecular systems, but molecular systems are a little bit different in as much as actually, they're not that different. they're not that different in terms of the thermodynamics. The big difference between molecular systems and solid systems are the kinetics, and we're not going to talk about that in detail. We might get into that toward the very end. What can you do with phase diagrams? But so if you're interested in molecular systems and you're interested in the thermodynamics of mixing and phases, then this will also work for you. Other questions? Great. Well, then I will send out the syllabus version 1.1 and see you on Wednesday.